both the sections, and some disturbance I think you may found outside the like here some borewell. I think they're digging the borewell, I guess. That sound it may come. Okay, so here I think in the last class we were discussing about the directed graph and the types of relation. So in that types of relations we have done up to a symmetric relation. Now let's go ahead with today's discussion, that is all about the transitive relation. So here, and G section people, don't worry, I'm recording it in H section. Okay, in one section I'll be recording. So here, the transitive is actually basically, it is like, say there is if suppose A is a friend of B and B is say if I take A is a friend of B and B is friend of C, then A must be friend of C. So that's what it is, a short you can say the idea about the transitive relation. So what is this transitive relation is all about? A relation R on a given set A, it is said to be transitive whenever A is related to B and B is related to C. If these two conditions are satisfied, then we say that AB and BC belongs to R, then AC also must be belongs to R. Means A is related to B, B is related to C. It should imply A is related to C. So that should happen. Then we call it as transitive. We say that R is not transitive if there exists some ABC such that these two belongs to R, AB and BC belongs to the relation, but AC does not belongs to the relation. If this is happening, we say that the given relation is not transitive. So in order to become transitive, all this condition must holds true. That is, A and B should be related, B and C should, and then along with that A and C must also should be related. If this fails, we call it as not transitive. Let's see. Determine which of the relations on this set, this given set, are transitive. So the R1 is given to us, R2 is given, R3 is given, R4 and R5 are given. So in R1, if you see carefully, okay, so they're asking us which of the relations are transitive. So here, 1 1 you have. So 1 is again 1 1. 1 1 is related to 1 1, like A and B are one another same here. So 1 is related to 1, again 1 is related to 1. So 1 is related to 1, no worry. 1 is related to 2 here and 2 is related to 3 here. That must be 1 also should be related to 3. That means there is a observation you can observe. 1 is related to 2, 2 is related to 3, hence 1 has to be related to 3. So that is available. Similarly, 1 is related to 3. So here there is no nothing like 3 is related to something. So no worry. So 4 is related to 4. That implies you have this observation. So clearly it is a transitive relation. Similarly, you can see R2. So here R2, 1 is related to 1 is there. 1 is related to 2. 2 is related to 1. That means 1 must be related to 1. That is there. Then 1 is related to 2. Your 2 is related to 2. You can see 2 is related to 2. That means 1 has to be related to 2. So 1 is related to 2 is available. So go with 2 is related to 1. 1 is related to 2. Okay. So here you can see 2 is related to 1. Then this 1 is related to 2. That means 2 must be related to 2. So it is here. Similarly, 2 is related to 1. 1 is related to 1. That means 2 must be related to 1. Again, that 2 related to 1 is there. So you should check for each and every element. You just can't decide it only with the 1 or 2 element. You just, if I say 1 is related to 2 is there, 2 is related to 1 is there, hence 1 is related to 1 is there. So it is transitive. No. You should see for each and every possibility is available. So clearly you can see in this example, here 1 and 2 are related, 2 and 1 are related, hence 1 and 1 are related. Similarly, 2 and 1 are related, 1 and 2 is also related, 1 and 1 is here. So you can see 2 is related to 1. Okay, you can come back and you can see 2 and 2 is related, 2 is again related to 1, therefore 2 must be related to 1, so it is here. Similarly, 3 related to 3, 4 related to 4 is available. Hence, R2 is also a transitive relation. But come to the R3. So here if you see R3, here 1 is related to 3 is there. There is no, question of 3 is related to something. Similarly, 2 is related to 1 is there. So this 1 is related to 3, but 1 is not related to 1. You can see 2 is related to 1, 1 is related to 3. But here you have 1 is related to 1 is missing. So this particular pair is not available in the R3. Hence R3 is not a transitive relation. So clearly you can see 2 is related to 1, 1 is related to 3 belongs to R3, but 2 related to 3 does not belongs to R3. Okay. So like this, you can just observe the given set of relations. Similarly here, it's not 1 related to 1, it has to be 2 related to 3, sorry. Okay, then R4 is an empty relation, so there is no such elements which are present or which are absent, because of which we can tell that it is not belongs to, hence it is always transitive. And universal relation, as you know, it contains all the possible pairs of relation, hence it is always transitive relation. So what is not transitive here? R3 is not transitive. Okay, so like this you should see the problems and you should analyze which are related, which are not related. Okay, now see, all of you just take this example. Determine which of the
Ma'am,
relations. Yes.
excuse me,
Yeah.
ma'am.
Yeah.
Ma'am, then the reflexive function will be transitive only, no, ma'am?
Yes, you are absolutely correct. Reflexive function will be always transitive. Like see, if you take 1, 1, 2, 2, 3, 3, 4, 4. So 1 is related to 1, 1 is further related to 1. So 1 is related to 1. Correct? And again 2 is related to 2, 2 is again related to 2, means every reflexive function is always a transitive function. Okay?
Yeah, ma'am.
Yeah. Now see this example, less than or equal to subset. These notation you must know. Okay, so in the DMS it is very important to know the notations. So I'll just tell you this notation you all are familiar with. This is less than or equal to, whereas this is subset or equal to. That means it may be subset or it may be equal. For that we use. Yes,
I think you're not recording the class.
I have been recording in one section.
Okay, ma'am.
I told you in the beginning, right?
You told in H section, so.
Howda. In G section is it going on? Because
Yes, ma'am.
it record, yeah, in one section it is going on, beta. Sorry.
Okay, ma'am.
Okay. So it is subset or equal to. So subset or equal to, be careful. Subset means it may be like, say, for example, I say A is equal to 1, 2 and B is equal to, say, 1, 2, 3. So in this case, A is clearly subset of B. Whereas when I say A is equal to 3, 1, 2, 3 and B is also equal to 1, 2, 3, then it is subset or equal to. Means it is equal. If it contains all the 3 elements here, then it is equal. So be careful when you are using the symbols. Okay. And they are asking that they are transitive. Let's see. If A is subset or equal to B, or here if you say less than, if A is less than or equal to B, and B is less than or equal to C, then A must be less than or equal to C. Can you take one example now? Say for example, 2 is less than or equal to 3. Okay, I may not take equal to, but less than 3 for example. And similarly, your 3 is less than or equal to 4. Then obviously 2 must be less than or equal to 4. Correct? So if you take less than, strictly you go ahead with that. So this equal to symbol when you take, if you're taking same, here also you're taking same, here also you're taking same. If you just strictly want to take, just simply you can just write 2 is less than 3 and 3 is less than 4, so 2 is less than 4. Okay, so it is always transitive. Similarly, subset, A is subset or equal to B and B is subset or equal to C, then A must be subset or equal to C. Okay, so these relations, less than or equal to and subset or equal to, they're always transitive relation. Okay, now clearly one more example you see, if A divides B and B divides C, so A divides C, is it true? Is it true or not? If 2 divides 4, and 4 divides 8. So 2 must divides 8, right? Are you following
Yes,
me?
ma'am.
Yes, ma'am. Yes,
Yeah,
ma'am.
so like that. Okay. So then one more example. If you see in the geometrical way, if I have perpendicularity, say perpendicularity is not a transitive relation because this line if I consider, so this is perpendicular to this line. So this is my line A and this is my line B. So A is perpendicular to B and B is perpendicular to say C line. Is it A and C are perpendicular, guys?
Yes.
A
Perpendicular?
and C are parallel.
No, ma'am.
No. So therefore, the perpendicularity is not transitive. Okay. So though A is perpendicular to B and this B is perpendicular to C, but A and C are not perpendicular. But parallelism, if you see, what about parallelism? So here A you have, if A is parallel to B, okay, so this is my line A and this is my line say B. If there are two lines, if A is parallel to B, okay, if I say A is parallel to B and B is parallel to A, what has to be the next relation? It has to be A parallel to A, right? Is
C.
it every line is parallel to itself? No. Please remember, here you may do the mistake. So therefore, since no line is parallel to itself, we can have only A is parallel to B and B is parallel to A, but A is not parallel to A. Hence, thus parallel is also not transitive. If it is fails for one particular element, it has to fail. If you take here C, it will valid. A is parallel to B and B is parallel to C, hence A is also parallel to C. But if I take only two lines, then it will fail. If it is failed for one line, then you cannot generalize it. This is the importance. Are you following, guys?
Yes, ma'am.
Yeah. Though if you are taking different lines, you may come to the conclusion. But when you take only two lines and you want to generalize it, it fails. Okay? So that's why. And there is one theorem. A relation R is transitive if Rn means R dot R dot R dot up to Rn times. Okay. So Rn is subset or equal to R for every n greater than equal to 1. That means here R square is subset or equal to R, your R cube is subset or equal to R, and so on and so forth. So clearly R square means R dot R, and more generally if you want to write, your Rn can be written as Rn minus 1 into R. If you want to write R2, it is nothing but R into R. If you want to write R3, it is R square dot R, and so on. So this relation is transitive. Anytime if you want to say that it is transitive, whenever this R cube has to be a subset or equal to R. If you take R4, it has to be subset or equal to R. So like that, if in general Rn is there, that has to be subset or equal to R. If it is happening, then we say that it is always a transitive relation. Okay, so this is one of the property in terms of theorem. So in generally, we can quote. So now there are some important properties like closure properties. So we say that in addition, subtraction, we say that addition is closed under the real line. Addition, subtraction is closed under the real line. The same way in this discrete mathematics also, we have some closure properties. So let's understand what is the closure properties are all about. So here, consider a given set A and the collection of all the relations on A. So I'm considering one set A and I'm considering all the possible relations. Okay, so it is taking all relations. So all relations we are taking. Let we take P be a property of such relations. So there is some property P such as it has to be being symmetric or it has to be being transitive. So what property it talks about? It talks about either symmetric or it has to be transitive. A relation, whatever the relation I'm considering, so there is this relation with this property, whether the symmetric property or transitive property is called as P relation. So what this definition is talking about, there is a set A and I will consider a collection of all the relations here. So on this set A, I'm taking all the possible collections. On this R, I consider one property, whether it has to be symmetric. Being symmetric means it has to be symmetric or it has to be transitive, any one of the relation. Then this relation together with this property is called as P relation. Are you following, guys, the definition?
Yes, ma'am.
Yes, ma'am.
Okay, so now what is this P closure then? The P closure of an arbitrary relation. Arbitrary relation means any relation. I may choose arbitrarily any number. So like that, arbitrarily I may choose any relation. As you know, on a given set, there are many relations are possible. So out of that, I may choose any arbitrary relation R on the given set A. So that will be written as P of R. P of R. So P of R means you know that it is a P relation. P relation means you know that it may be being symmetric or it may be being transitive. So this all should this is all the background. Okay. If you know this, then this P relation is such that your given relation must be subset or equal to the P relation, and this must be the subset of the given set S. So what is this set S? This set is nothing but it is a subset of this R. So this way you are denoting. This way you are denoting. So here by denotion what it is actually indicate is we are taking any arbitrary relation P of R which is a subset of R. Subset means you can see R is subset of P of R. Okay. And this P of R is in turn the subset of S. So where this S is containing what? So S is the biggest set here. So S is the bigger set which is containing this relation also, and this is containing P relation also. So like this you can imagine. So this is a given set. This is the biggest set which I'm talking about. So this is a given set S, and here is your P of S. This is your P of S, and here is your relation R. So here R, this is subset of P of S, and this P of S is subset of S. Are you able to imagine how the set it may be?
Yes, ma'am.
So here we write reflexive R. So relation means we write reflexive in bracket R, symmetric of R, and transitive of R for the reflexive, symmetric, and transitive closure. So when you want to write for a closure, so you will write it as reflexive in bracket R, symmetric in bracket R, and transitive in bracket R. So this is the notation which you are supposed to remember. It will be more clear when we solve some examples on it. Okay. So let's see. Let's understand the theory first. So reflexive and symmetric closure. So here delta A is defined as A comma A where A belongs to A. So here A comma A means A is related to A. For every element coming from the given set A is defined as delta A. It is diagonal, or it is also called equality relation on given set A. So it is not, we will focus, this particular result, wherein we will understand what exactly this reflexive and symmetric closure is all about. Let's see. Let R is the relation on a given set A, then your given set R union delta A. So union delta A means delta A is nothing but it is this relation where A comma A is related for every element belongs to A. This is reflexive closure of R. So reflexive closure of R means let R may be any relation. Let R may be any relation. If I include this reflexive elements, so reflexive elements means for example 2, 2, 1, 1, 3, 3, all elements if I am including, then definitely that relation will become what? Reflexive relation. Hence this R union delta A will become reflexive closure. So why do we use this closure property? I'll tell you. So sometimes we will not be having a reflexive relation. So to convert the non-reflexive or irreflexive relation into the reflexive one, we utilize them as the properties. So these are the properties which will convert the non-reflexive one to the reflexive. Thus we call that as the closure, reflexive closure. Reflexive closure means it is becoming reflexive. Symmetric closure means it is becoming symmetric. Before it was not symmetric. Now by doing so, it is becoming symmetric. Are you following me? Why the
Yes, ma'am.
closure properties were required is So sometimes we will not be having what we want. So for that, we should convert by doing some additional operation. So this closure operation is the additional operation in order to convert the non-reflexive, or you can say irreflexive one to the reflexive. So here, by including this one, our union, whatever the relation is given, if I include all the reflexive elements here, it automatically become reflexive closure. Similarly, universe, R union, R inverse. You know that inverse means suppose if suppose your R is containing 1, 2, okay, and your R inverse will be automatically 2, 1. So that implies it is always containing A is related to B, then B is related to A. So therefore, it will become what? Symmetric. So hence, by including this inverse, we will make it as symmetric closure. So by including the reflexive elements, we are making it as reflexive closure, whereas by including the inverse, we are making it as symmetric closure. In the other words, reflexive R is obtained by simply adding to R those elements of this form in the diagonal which do not already belong to R. Okay, so that means what we're adding them separately and we're making it reflexive. Similarly, symmetric R is nothing but by obtaining or by adding R to all pairs of B comma A. Whenever you have A comma B belongs to R. So suppose you have A comma B in R, its inverse will be what? B comma A. By adding that, it will become what? Symmetric. Are you following the relation? I mean, the sequence, guys, what we are doing here? Don't bother about the theory. Try to understand the concept. What we are doing. Okay, the closure property, wind up, I'm telling you, what is this closure property is doing is, in some of the relations, when you deal with a big relations, big sets, so sometimes reflexive is mandatory and symmetric is mandatory and transitive is mandatory. So if we don't have that, so we will convert it by using the closure property. How do we do that? By taking the additional elements, by taking the union with the reflexive elements, by taking the union with the inverse elements, we can convert that into the reflexive closure and symmetric closure. Hence, we can achieve it. Am I clear up to this theorem, guys? If anybody has questions, anything, please let me know. Am I clear? Guys?
Yes, ma'am.
Yes,
Sleeping? Malukbedro, it's a morning class. Okay, so now see the example here. Consider the following relation on this given set. Okay, A is equal to 1, 2, 3, 4. So R is given as 1, 1, 1, 3, 2, 4, 3, 1, 3, 3, and 4, 3. So what we are, in order to make it as a reflexive R, what we need, guys? Can you just tell me? The reflexive R will be equal to, here you can see 1, 1 is there and 3, 3 is there. Still what we want? Still what we have to add so that it will become reflexive R? Yes?
2, 2
2, and 4, 4. Yes. So therefore, we are writing here R union 2, 2 and 4, 4. So this is our reflexive R. So this is our reflexive R. Then in this particular relation will become, this will become the closure under the reflexive relation. Similarly, in order to become the symmetric, you can observe 1, 3 is here, 3, 1 is here, no issue. 2, 4 is here, but 4, 2 is it there? No. Similarly, 4, 3 is there, 3, 4 is also not there. So we should add those two elements. So hence, R union 4, 2 and 3, 4. So this will be the symmetric of R. This will be the symmetric of R. Are you following the example?
Yes, ma'am.
Okay.
Yes, ma'am.
So now consider the relation less than on the natural number set. Natural number set, or we can also call it as positive integers. Then reflexive less than will be equal to, so less than of all the elements. So here you can see A comma B such that A is less than B. If this is a relation, if you are defining, this will be reflexive under the less than symbol. So that means 2 is less than 3, 3 is less than 4, 4 is less than 5, and so on. You take any pair of this kind that will be valid under this. Similarly, for symmetric, if you take this, is it possible? Is it possible if I take in this way, where A and B must be what? They must be different. They must be different. Like say, if I say 2 is less than 3, then 3 must be less than 2. Then only I can say it is symmetric. Therefore, it is not valid here. Okay. So therefore, only this reflexive, consider this reflexive relation for the less than integer on, and just some of you just take up this symmetric and reflexive and work on it and get back to me tomorrow. I think it's already 9:40, so we will leave the class here. Okay. So in tomorrow's discussion, we will continue with the, that is, how do we understand the closure of transitive relations and some examples related to it. If you have any questions, anything, please get back to me, and just don't leave the meeting. Let me take your attendance. Okay, just give me one moment. I'll be taking your attendance. Yeah. Okay, guys, you can leave now. 1 minute. I'll just stop recording. In this section I was doing, you can leave the meeting. See you guys. Please take care. Don't go out. See you soon. Take care.
Thank you.
Yeah.